following content is provided under a Creative Commons license. Your support will help MIT OpenCourseWare continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseWare at ocw.mit.edu.
So, again, welcome to 1801. We're getting started today with what we're calling Unit 1, highly imaginative topic, highly imaginative title, and it's differentiation. So let me first tell you briefly what's in store in the next couple of weeks. The main topic today is what is a derivative. And we're going to look at this from several different points of view. And the first one is the geometric interpretation. And that's what we'll spend most of today on. And then we'll also talk about a physical interpretation of what a derivative is. And then there's going to be something else which I guess is maybe the reason why calculus is so fundamental and why we always start with it in most science and engineering schools, which is the importance of derivatives of this to all measurements. So that means pretty much every place. That means in science, in engineering, in economics, in political science, etc. Polling, lots of commercial applications, just about everything. Now, so that's what we'll be getting started with. And then there's another thing that we're going to do in this unit, which is we're going to explain how to differentiate anything. So how to differentiate any function you know. And that's kind of a tall order, but let me just give you an example. If you want to take the derivative, this we'll see today as the notation for the derivative of something, of some messy function like e to the x arctan of x, we'll work this out by the end of this unit. All right? So anything you can think of, anything you can write down, we can differentiate it. All right, so that's what we're going to do. And today, as I said, we're going to spend most of our time on this geometric interpretation. So let's begin with that. So here we go with the geometric interpretation of derivatives. And what we're going to do is just ask the geometric problem of finding the tangent line to some graph of some function at some point, which is, say, x0, y0. So that's the problem that we're addressing here. I guess I should probably turn this off. All right. So here's our problem. And now let me show you the solution. So, well, let's graph the function. So let's say here's its graph. And here's some point. All right. Maybe I should draw it just a bit lower so that I don't. All right, so here's a point P. Maybe it's above the point x0. x0, by the way, this was supposed to be an x0. That was some fixed place on the x-axis. And now, in order to perform this mighty feat, I will use another color of chalk. How about red? Okay, so here it is. There's the tangent line. Well, not quite straight, close enough. All right, I did it. All right, that's the end. That's the geometric problem. I achieved what I wanted to do. And it's kind of an interesting question, which unfortunately I can't solve for you in this class, which is how did I do that? That is, how physically did I manage to know what to do to draw this tangent line? But that's what geometric problems are like. We visualize it, we can figure it out, somewhere in our brains it happens. And the task that we have now is to figure out how to do it analytically, to do it in a way that a machine could do just as well as I did in drawing this tangent line. So what did we learn in high school about what a tangent line is? Well, a tangent line has an equation. Any line through a point has the equation y minus y0 is equal to m, the slope, times x minus x0. So here's the equation for that line. And now there are two pieces of information that we're going to need to work out what the line is. The first one is the point. That's that point P there. And to specify P, given x, we need to know the level of y, which is, of course, just f of x0. Now, that's not a calculus problem, but anyway, that's a very important part of the process. So that's the first thing we need to know. And the second thing we need to know is the slope. And that's this number m. And in calculus, we have another name for it. We call it f prime of x0, namely the derivative of f. So that's the calculus part. That's the tricky part. And that's the part that we have to discuss now. So just to make that explicit here, I'm going to make a definition, which is that f prime of x0, which is known as the derivative of f at x0, all right, is the slope of the tangent line to y equals f of x at the point, let's just call it P. All right? So that's what it is, but still I haven't made any progress in figuring out any better how I drew that line. So I have to say something that's more concrete because I want to be able to cook up what these numbers are. I have to figure out what this number m is. And one way of thinking about that, let me just try it, is, so I certainly am taking for granted that in sort of non-calculus part that I know what a line through a point is. So I know this equation. But another possibility might be, you know, this line here. How do I know? Well, unfortunately, I didn't draw it quite straight, but there it is. How do I know that this orange line is not a tangent line, but this other line is a tangent line? Well, it's actually not so obvious, but I'm going to describe it a little bit. It's not really the fact, this thing crosses at some other place. which is this point Q. But it's not really the fact that the thing crosses at two places, because the line could be wiggly, the curve could be wiggly, and it could cross back and forth a number of times. That's not what distinguishes the tangent line. So I'm going to have to somehow grasp this, and I'll first do it in language. And it's the following idea. It's that if you take this orange line, which is called a secant line, and you think of the Q, the point Q is getting closer and closer to P, then the slope of that line will get closer and closer to the slope of the red line. And if we draw it close enough, then that's going to be the correct line. So that's really what I did sort of in my brain when I drew that first line. And so that's the way I'm going to articulate it first now. So the tangent line is equal to the limit of what so-called secant lines, PQ, as Q tends to P. And here we're thinking of P as being fixed and Q as varying. All right, so that's again, this is still a geometric discussion, but now we're going to be able to put symbols and formulas to this computation, and we'll be able to work out formulas in any example. So let's do that. So first of all, I'm going to write out these points P and Q again. So maybe we'll put P here and Q here. And I'm thinking of this line through them. I guess it was orange, so we'll leave it as orange. All right. And now I want to compute its slope. And so this will gradually, we'll do this in 2 steps, and these steps will introduce us to the basic notations which are used throughout calculus, including multivariable calculus, across the board. So the first notation that's used is, you imagine here's the x-axis underneath, and here's the x0, the location directly below the point P. And we're traveling here a horizontal distance, which is denoted by delta x. So that's delta x, so-called. And we could also call it the change in x. All right, so that's one thing we want to measure in order to get the slope of this line PQ. And the other thing is this height. So that's this distance here, which we denote delta f, which is the change in f. And then the slope is just the ratio delta f over delta x. So this is the slope of the secant. And the process I just described over here with this limit applies not just to the whole line itself, but also in particular to its slope. And the way we write that is the limit as delta x goes to 0, and that's going to be our slope. So this is the slope of the tangent line. Okay, now this is still a little general, and I want to work out a more usable form here. I want to work out a better formula for this. And in order to do that, I'm going to write delta f, the numerator, more explicitly here, the change in f. So remember that the point P is the point x0, f of x0. All right, that's what we got from our formula for the point. And in order to compute these distances, and in particular the vertical distance here, I'm going to have to get a formula for Q as well. So if this horizontal distance is delta x, then this location is x0 plus delta x. And so the point above that point has a formula, which is x0 plus delta x, f of, and this is a mouthful, x0 plus delta x. All right, so there's the formula for the point Q. Here's the formula for the point P. And now I can write a different formula for the derivative, which is the following. So this f prime of x0, which is the same as m, is going to be the limit as delta x goes to 0 of the change in f. Well, the change in f is the value of f at the upper point here, which is x0 plus delta x, and minus its value at the lower point, p, which is f of x0, divided by delta x. All right, so this is the formula. I'm going to put this in a little box because this is by far the most important formula today, which we use to derive pretty much everything else. And this is the way that we're going to be able to compute these numbers. So let's do an example. This example, so we'll call this example 1. We'll take the function f of x, which is 1 over x. That's sufficiently complicated to have an interesting answer, and sufficiently straightforward that we can compute the derivative fairly quickly. So what is it that we're going to do here? All we're going to do is we're going to plug in this formula here for that function. That's all we're going to do. And visually, what we're accomplishing is somehow to take the hyperbola and take a point on the hyperbola and figure out some tangent line. All right, that's what we're accomplishing when we do that. So we're accomplishing this geometrically, but we'll be doing it algebraically. So first, we consider this difference, delta f over delta x, and write out its formula. So I have to have a place, so I'm going to make it, again, above this point x0, which is a general point. We'll make the general calculation. So the value of f at the top, when we move to the right by f of x, so I just read off from here the formula. The first thing I get here is 1 over x0 plus delta x. That's the left-hand term, minus 1 over x0. That's the right-hand term. And then I have to divide that by delta x. Okay, so here's our expression. And by the way, this has a name. This thing is called a difference quotient. It's pretty complicated because there's always a difference in the numerator, and in disguise the denominator is a difference because it's the difference between the value on the right side and the value on the left side here. Okay, so now we're going to simplify it by some algebra. So let's just take a look. So this is equal to, let's continue on the next level here. This is equal to 1 over delta x times, now all I'm going to do is put it over a common denominator. So the common denominator is x0 plus delta x times x0. And so in the numerator for the first expression, I have x0 And for the second expression, I have x0 plus delta x. So this is the same thing as I had in the numerator before, factoring out this denominator. And here I put that numerator into this more amenable form. And now there are two basic cancellations. The first one is that x0 and x0 cancel. So we have this. And then the second step is that these two expressions cancel, right? The numerator and denominator. Now we have a cancellation that we can make use of. So we'll write that under here. And this is equals minus 1 over x0 plus delta x times x0. And then the very last step is to take the limit as delta x tends to 0. And now we can do it. Before we couldn't do it. Why? Because the numerator and the denominator gave us 0 over 0. But now that I've made this cancellation, I can pass to the limit. And all that happens is I set this delta x equal to 0, and I get minus 1 over x0 squared. All right, so that's the answer. All right, so in other words, what I've shown, let me put it up here, is that f prime of x0 is minus 1 over x0 squared. Now, let's look at the graph just a little bit to check this for plausibility, all right? What's happening here is, first of all, it's negative, right? It's less than 0, which is a good thing. You see that slope there is negative. That's the simplest check that you could make. And the second thing that I would just like to point out is that as x goes to infinity, that is, as we go farther to the right, it gets less and less steep. So less, and whoops, as x0 goes to infinity, not 0. As x0 goes to infinity, less and less steep. So that's also consistent here. As when x0 is very large, this is a smaller and smaller number in magnitude, although it's always negative. It's always sloping down. All right. So I've managed to fill the boards, so maybe I should stop for a question or two. Yes? So the question is to explain again this limiting process. So the formula here is we have basically two numbers. So in other words, why is it that this expression, when delta x tends to 0, is equal to minus 1 over x0 squared? Let me illustrate it by sticking in a number for x0 to make it more explicit. All right? So for instance, let me stick in here for x0 the number 3. Then it's minus 1 over 3 plus delta x times 3. That's the situation that we've got. And now the question is, what happens as this number gets smaller and smaller and smaller and gets to be practically 0? Well, literally what we can do is just plug in 0 there. Then you get 3 plus 0 times 3 in the denominator, minus 1 in the numerator. So this tends to minus 1 over 9, over 3 squared. And that's what I'm saying in general with this extra.
But I can't help my